Okay, let's try this again. This is my third attempt having some technical difficulties today. So I'm going to try to get you through section 11-2 on our digital learning day. Hopefully you'll save some time to go out and play in the snow or the rain, as the case may be. Alright, so section 11-2. It's going to be talking about torque and its ability to cause an angular acceleration. We've been doing torque and equilibrium, but for sections 11.2 and 11.5, we're going to have a net torque that's going to cause angular acceleration, and we'll have to take care of the problems that come up with that. Okay, so for today's digital learning, I'm going to go through all the blanks and the examples in section 11-2. So a single torque acting on an object will cause an angular acceleration alpha. When a force acts on a mass that's attached to the light rod, and we've got a picture down here, the force will cause the mass at the end of the rod to accelerate. But that force is also going to create a torque that causes the rod and the mass to experience an angular acceleration about the pivot. So it's the same exact force, and if we looked at just the force attached to the mass, then we would say that the force will cause that mass to accelerate. So it's going to cause it to speed up in this tangential direction. Now there has to be an additional force if that mass is going to be able to go in a circle, and that force would be caused by the tension in the rod, something pulling it towards the center. But that force also creates a torque about this. If we call that our pivot, then it's causing a torque which is causing everything to then accelerate around the pivot in an angular fashion. Okay? So when a force is applied tangent to the circle as shown above, then the torque produced by that force, because by definition it's going to be perpendicular to that radius, is just equal to the force times the radius. In the space below, write the equation that relates the net torque, the moment of inertia, and the angular acceleration. And that would be that the sum of torque, or the net torque, will cause an object that has a moment of inertia to accelerate angularly. Okay? So that's torque equals I alpha. This equation should look familiar in structure because it's related to Newton's second law, which said that if there was a net force, it would cause a mass to accelerate. If you just use the rotational, and the word is analog, but the rotational equivalent of each of the translational variables, then the rotational of equivalent for force is torque. Greek letter tau. The analog for mass is the moment of inertia, variable I, and the analog for acceleration is angular acceleration, and the variable for that is alpha. Okay. Now we just got some examples to look at. Okay. The first one's going to be a conceptual example that's from your book, Conceptual Checkpoint 11.1, and it's got two situations here where this hanging box is going to cause the wheel with this bar to rotate, and the box is going to fall. Okay, and the question is basically about which one of these boxes is going to hit the ground first. Well, if we think about this just from a moment of inertia standpoint, right? The torque on this one and the torque on this one are essentially the same, right? Because they're both being provided by the tension, which is close to the weight of the box. Okay, so the torques are the same. So their ability to accelerate is going to be a function of their moment of inertia. The larger the moment of inertia, the smaller the angular acceleration. So when we look at these two boxes, we remember that the moment of inertia for a point mass is mr squared. So the farther away it is, the larger the moment of inertia. So this one's going to have a larger moment of inertia than this one because the masses are closer to the pivot, which is here at the center of the wheel. Okay. So the larger the moment of inertia, the smaller the alpha, because it's got to be essentially the same torque. Okay. So the box on the right is going to hit the ground first, and that's because the system on the right has the smaller moment of inertia. Okay, so that's the conceptual, right? Now, if we take a look at example 7, we can put at least a proportional thinking to this. So it says the rod and the pulley that we have pictured above are essentially massless. So the pulley doesn't have mass, and they're saying the bar doesn't have any mass. But the point masses are going to be brought from the ends to halfway. And then by what factor, so this what factor tells you that this is a proportional thinking question, does the acceleration and the time to hit the ground change, assuming that the system was initially at rest when the mass begins to fall. So interesting question here in that we've been talking a lot about angular acceleration, but now they're asking us, well, what happens to the linear acceleration of the box as it falls? Well, let's remind ourselves that the linear acceleration is equal to, and I'm going to use a different variable for r. I'm going to use capital R alpha. And what I'm talking about here is the radius of the pulley. So the acceleration of this box is equal to the radius of the pulley, because that's what it's attached to, times alpha. This r is different than the r associated with where those point masses are. Okay? So whatever alpha does, A is going to do. Okay? So even though the question was about acceleration, we can really look at, well, what happens to alpha? Because whatever happens to alpha, the same thing's going to happen to A, because the radius of the pulley is not going to change. Okay? All right, so let's deal with what's changing. All right, so the radius is going to decrease by a factor of 2. We're going to cut the radius in half. Then our equation that we've got to deal with is that the net torque will cause an object with a moment of inertia to accelerate angularly. And our moment of inertia, because we have two masses, it's 2 times mr squared times alpha. Well, rule of ones says that we want to rearrange this equation for alpha. So alpha is equal to the net torque divided by 2 mr squared. If we apply the rule of ones to that now, the torque isn't going to change. 2 isn't going to change. The mass isn't going to change. But the radius is being cut in half, and it's squared. So when we square the 1/2, we get a quarter, but it's in the denominator, so we have to invert and multiply. So alpha is going to increase by a factor of 4. So as the moment of inertia gets smaller, when you pull the masses in, then the angular acceleration is going to go up by 4. If the angular acceleration goes up by 4, then the radius doesn't change. So the linear acceleration goes up by a factor of 4. All right? Now the other question was about time. Well, this is going to be a linear kinematic solution because the box is going to fall a distance d. So we've got d equals VIT plus 1/2 a t squared. The initial velocity is 0. So we want to, again, by rule of ones, we want to rearrange this to solve for the variable in question, which is time. Okay, so the time is equal to the square root of 2 times d divided by a. By rule of ones, the 2 doesn't change, the distance doesn't change, and the acceleration is increasing by a factor of 4. So the time gets cut in half. Okay, so by pulling the radius in by a factor of 2, or cutting it in half, the acceleration goes up by a factor of 4 and time goes down by a factor of 2, or gets cut in half. So you don't have any linear relationships here, right? One of them quadrupled and one of them got cut in half. All right, so that's example 7. So let's take a look at what we've got next. And again, we kind of have a proportional or conceptual example, and then we've got one that we can plug some numbers into. Example 8 says that a light 0.6 millimeter rod has a compact 500 gram mass attached to each end of the rod. The dotted line shows the position of the axis of rotation in the 3 different cases. Rank the 3 systems in order of increasing angular acceleration, assuming that equal amounts of torque are applied, and you may assume that the pictures are roughly to scale. Okay, so this may be a little hard to see, so I'll label the axis of rotation is here on this one. So this one is rotating this way. Then the axis of rotation is in the middle of this configuration. So it's a bar like this, and it's rotating about its center point. And then over here, the axis of rotation is on the far right-hand side. So it's going to rotate about that end. Okay. So we've got the axis of rotation in 3 different places, and they want us to rank it according to angular acceleration. So we probably should remind ourselves again that a net torque will cause something with a moment of inertia to accelerate angularly. So alpha, that they want us to rank this on, is then going to be the net torque divided by I. And they told us that the torque was constant for all of them. So the real question comes down to the moment of inertia. And it's an inverse relationship with alpha. So the bigger I is, the smaller alpha is going to be. And the smaller I is, the bigger alpha is going to be. So we really need to figure out what these moments of inertia are about their respective axes of rotation. So a couple things going on here. It's a light rod, which means we don't have to deal with the moment of inertia of the bar. And they're compact masses, meaning that, you know, they've shown them with some size, but there's no given radius for that, so we can assume that that's a point mass. Well, there's no distance from these masses to this axis of rotation. So the moment of inertia for this one is going to be 0, because the equation is mr squared and we've got no r. There is no distance away from that axis of rotation. So if I is 0, then alpha is going to be a very large number. You know, mathematically, arguably, we could say it was going to infinity. Okay. So let's look at the I for this one. Okay. So the I have two masses that are going to be rotating. So the sum of my moment of inertia is 2 times whatever the moment of inertia is for one of them. Okay. Which is going to be m times its distance away from the axis, which is half the radius, or r over 2, and it's squared. So if we square this, we'd have r squared over 4, so we have 2 over 4, so this is going to be a total of m r squared over 2 for that moment of inertia. Then if we look on this side, well, this object is on the axis of rotation. So again, the radius for this mass is 0, so it's not going to do anything moment of inertia wise, so we just have to look at the moment of inertia of the far left-hand object. So I for that is equal to m, and it's a full radius away. So we have 1m at an r away, and it's squared. So this moment of inertia is twice as much as this one. And this one's bigger than this one. So this is my largest moment of inertia, my middle, and my smallest. So I'll just say I here is large, I here is middle, and I here is small. And because it's an inverse relationship, right, then alpha over here is going to be small. Alpha here is going to be in the middle. And alpha over here is going to be large. Okay, so my ranking on alpha is small, middle, large, and increasing order. All right, then our last example, example 9. A saw blade accelerates from rest to 3,000 RPM in 1.25 seconds. If the blade has a radius of 15 centimeters and a mass of 300 grams, what is the torque of the motor? So what is it that's going to get this thing up to this speed in that amount of time? Assume that the blade can be treated as a uniform disc. So start with something that can answer the question. What's the torque? So the net torque is what will cause an object with a moment of inertia to accelerate angularly. So because they said this is a uniform disk, I can look that up in table 10-1, and I would know that I is 1/2 mr squared times alpha. So I've got 1/2. The mass is a given. It's 300 grams, but we have to convert that to kilograms. So that's 0.3 kilograms. The radius is given at 15 centimeters, and we have to convert that to meters. That's 0.15 meters, and that's squared. And the only thing keeping us from solving this is we don't know what alpha is. So if we could figure out alpha, then we can easily answer the torque question. So if we go back to the problem, we've got some kinematic information here. It starts from rest. So omega I is 0. It gets up to a speed of 3,000 RPM. So omega F is 3,000 revolutions per minute, and we're going to have to convert that to radians per second. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So if we do a little calculator abuse on that, we would get 314 radians per second. The time is 1.25 seconds, and alpha is what we need to know. So the kinematic equation, omega F equals omega I plus alpha T. So 314 is equal to 0 plus alpha times 1.25. So if we divide both sides by 1.25, then we would get that alpha, again a little calculator abuse, is 251 radians per second squared. And that was the piece of information that we needed to go in here. So times 251. More calculator abuse, and the net torque should turn out to be 0.85 Newton meters. So not a lot of torque, surprisingly not very much torque, to be able to get up to 3,000 RPM in 1 second. But the moment of inertia of this is also not very big. So if we were to calculate just that part, that's going to be a fairly small number for the moment of inertia. So then it doesn't take much torque to produce that kind of an alpha to get us to that kind of an RPM in 1 1/4 seconds. Okay, so that's your instruction for section 11-2. I'll get this posted, put a link to it in eClass, and open up the My Physics assignment on section 11-2, and hopefully I'll see you tomorrow. Thank you.